In this next series of videos, we'll get some more practice applying the divide and conquer algorithm design paradigm to various problems. This will also give us a glimpse of the kinds of application domains to which it's been successfully applied. We're going to start by extending the merge sort algorithm to solve a problem involving counting the number of inversions of an array. Before we tackle the specific problem of counting the number of inversions in an array, let me say a few words about the divide and conquer paradigm in general. So again, you've already seen the totally canonical example of divide and conquer, namely merge sort. So the following three conceptual steps will be familiar to you. The first step, no prizes for guessing, is you divide the problem into smaller subproblems. Sometimes this division happens only in your mind. It's really more of a conceptual step than part of your code. Sometimes you really do copy over parts of the input into, say, new arrays to pass on to your recursive calls. The second step, again, no prizes here, is you conquer the subproblems just using recursion. So for example, in merge sort, you conceptually divide the array into two different pieces, and then you recursively conquer or sort the first half of the array, and you do the same thing with the second half of the array. Now, of course, it's not quite as easy as just doing these two steps, dividing the problem and then solving the subproblems recursively. Usually you have some extra cleanup work after the recursive calls end to stitch together the solutions to the subproblems into one for the big problem, the problem that you actually care about. Recall, for example, in merge sort, after our recursive calls, the left half of the array was sorted, the right half of the array was sorted, but we still had to stitch those together and merge into a sorted version of the entire array. So the third step is to combine the solutions to the subproblems into one of the original problem. Generally, the largest amount of ingenuity happens in the third step. How do you actually quickly combine solutions to subproblems into one to the original problem? Sometimes you also get some cleverness in the first step with division. Sometimes it's as simple as just splitting an array in two, but there are cases where the division step also has some ingenuity. Now let's move on to the specific problem of counting inversions and see how to apply this divide and conquer paradigm. So let me begin by defining the problem formally. We're given as input an array A of length n, and you could define the problem so that the array A contains any old distinct numbers, but let's just keep things simple and assume that it contains the numbers 1 through n, the integers in that range in some order. That captures the essence of the problem. And the goal is to compute the number of inversions of this array. So what's an inversion, you may ask? Well, inversion is just a pair of array indices I and j with I smaller than j, so that the earlier array entry, the ith entry, is bigger than the later one, than the jth one. So one thing that should be evident is that if the array contains these numbers in sorted order, if the array is simply 1, 2, 3, 4, all the way up to n, then the number of inversions is 0. The converse you might also want to think through: if the array has any other ordering of the numbers between 1 and n other than the sorted one, then it's going to have a non-zero number of inversions. Let's look at another example. So suppose we have an array of 6 entries, so the numbers 1 through 6 in the following order: 1, 3, 5, followed by 2, 4, 6. So how many inversions does this array have? So again, what we need to look for are pairs of array entries so that the earlier or left entry is bigger than the later or right entry. So one example which we see right here would be 5 and 2. Those are right next to each other and out of order. The earlier entry is bigger than the other one. But there's others. There's 3 and 2, for example. Those are out of order. And 5 and 4 are also out of order. And I'll leave it to you to check that those are the only 3 pairs that are out of order. So summarizing, the inversions in this array of length 6 are 3, 2, 5, 2, and 5, 4, corresponding to the array entries 2, 4, 3, 4, and 3, 5. Pictorially, we can think of it thusly. We can first write down the numbers in order, 1 up to 6, and then we can write down the numbers again, but ordered in the way that they're given in the input array. So 1, 3, 5, 2, 4, 6. And then we can connect the dots, meaning we connect 1 to 1, we connect 2 to 2, and so on. It turns out, and I'll leave it for you to think this through, that the number of crossing pairs of line segments precisely correspond to the number of inversions. So we see that there are 1, 2, 3 crossing line segments, and these are exactly in correspondence with the 3 inversions we found earlier: 5 and 2, 3 and 2, and 5 and 4. Now, why might you want to solve this problem, you might ask? Well, there's a few reasons it comes up, but one would be to have a numerical similarity measure that quantifies how close two different ranked lists are to each other. So for example, suppose I took you and a friend and I identified 10 movies that both of you had seen. And I asked each of you to rank these movies from your most favorite to your least favorite. Now I can form an array and compute inversions, and it quantifies in some sense how dissimilar your two rankings are to each other. So in more detail, in the first entry of this array, I would put down the ranking that your friend gave to your favorite movie. So if you had your favorite movie, Star Wars or whatever, and your friend only thought it was the 5th best out of the 10, then I would write down a 5 in the first entry of this array. Similarly, I would take your second favorite movie, I would look at how your friend ranked that, I would put that in the second entry of the array, and so on, all the way up to the 10th entry of the array, where I would put your friend's ranking of your least favorite movie. Now, if you have exactly identical preferences, if you rank them exactly the same way, the number of inversions of this array would be 0. And in general, the more inversions this array has, it quantifies that your lists look more and more different from each other. Now, why might you want to do this? Why might you want to know whether two different people ranked things in a similar way, had similar preferences? Well, one reason would be in what's called collaborative filtering. So probably many of you have had the experience of going to a website, and if you've made a few purchases from this website, it starts recommending further purchases for you. So one way to solve that problem under the hood is to look at your purchases, look at what you seem to like, find other people who have similar preferences or similar history, look at things that they've bought that you haven't, and then recommend new products to you based on what similar customers seem to have bought. So this problem captures some of the essence of identifying which customers or which people are similar based on data about what they prefer. So just to make sure we're all on the same page, let me pause for a brief quiz. We've already noticed that a given array will have 0 inversions if and only if it's in sorted order, or if it only contains the numbers 1 through n in order. So on the other side, what is the largest number of inversions an array could possibly have? Let's say just for an array of size 6, like the one in this example here. So the answer to this question is the first one, 15, or in general, in an n-element array, the largest number of inversions is n choose 2. Also known as n times n minus 1 over 2, which again in the case of a 6-element array is going to evaluate to 15. The reason is the worst case is when the array is in backwards order, reverse sorted order, and then every single pair of array indices is inverted, and so the number of indices ij with I less than j is precisely n choose 2. Let's now turn our attention to the problem of computing the number of inversions of an array as quickly as possible. So one option which is certainly available to us is the brute force algorithm. And by brute force I just mean we could set up a double for loop, one which goes through I, one which goes through j bigger than I, and we just check each pair ij individually with I less than j whether that particular pair of array entities ai and aj is inverted. And if it is, then we add it to a running count. And then we return the final count at the end of the double for loop. That's certainly correct. The only problem is, as we just observed, there's n choose 2, or a quadratic number of potential inversions, so this algorithm is always going to run in time quadratic in the array length. Now remember the mantra of any good algorithm designer. Can we do better? And the answer is yes, and the method will be using divide and conquer. The way in which we divide will be motivated directly by merge sort, where we recur separately on the left and the right halves of the array. We're going to do the same thing here. To understand how much progress we can make purely using recursion, let's classify the inversions of array into one of 3 types. So suppose we have an inversion of an array I comma j. And remember, in an inversion you always have I less than j. We're going to call it a left inversion if both of the array indices are at most n over 2, where n is the array length. We're going to call it a right inversion if they're both strictly greater than n over 2. And we're going to call it a split inversion if the smaller index is at most n over 2 and the larger index is bigger than n over 2. We can discuss the progress made by recursion in these terms. When we recurse on the left half of an array, if we implement our algorithm correctly, we'll successfully be able to count all of the inversions located purely in that first half. Those are precisely the left inversions. Similarly, a second recursive call on just the right half of an array, the second half of an array, will successfully count all of the right inversions. There remains the question of how to count the split inversions, but we shouldn't be surprised there's some residual work left over even after the recursive calls do their job. That, of course, was the case in merge sort. Recursion magically took care of sorting the left half of the array, sorting the right half of the array, but there was still, after their return, the matter of merging those 2 sorted lists into one. And here again, after the recursion, there's going to be the matter of cleaning up and counting the number of split inversions. So for example, if you go back to the 6-element array we worked through before, 1, 3, 5, 2, 4, 6, you'll notice that there, in fact, all of the inversions are split. So the recursive calls will both come back counting 0 inversions, and all of the work for that example will be done by the count split inversions subroutine. So let's summarize where things stand and give an underspecified high-level description of the algorithm as we envision it. There is a base case. I'll go ahead and write it down for completeness, which is if we're given a 1-element array, then there's certainly no inversion, so we can just immediately return the answer 0. For any bigger array, we're going to divide and conquer, so we'll count the left inversions with a recursive call, the right inversions with a recursive call, and then we'll have some currently unimplemented subroutine that counts the split inversions. Since every inversion is either left or right or split and can't be any more than one of those three, then having done these three things, we can simply return their sum. So that's our high-level attack on how we're going to count up the number of inversions. And of course, we need to specify how we're going to count the number of split inversions. And moreover, we'd like that subroutine to run quickly. An analogy to merge sort, where outside the recursive calls we did merely linear work, in the merge subroutine. Here we'd like to do only linear work in counting up the number of split inversions. If we succeed in this goal, if we produce a correct and linear time implementation to count up the number of split inversions, then this entire recursive algorithm will run in big O of n log n time. The reason the overall algorithm will run in O of n log n time is exactly the same reason that merge sort ran in n log n time. There's 2 recursive calls, each on a problem of half the size, and outside of the recursive calls we would be doing linear work. So you could copy down exactly the same recursion tree argument we used for merge sort. It would apply equally well here. Alternatively, very soon we will cover the master method, and as one very special case it will prove that this algorithm, if we can implement it thusly, will run in O of n log n time. Now, one thing to realize is this is a fairly ambitious goal, to count up the number of split inversions in linear time. It's not that there can't be too many split inversions. There can actually be a lot of them. If you have an array where the first half of the array contains the numbers n over 2 plus 1 up to n, whereas the second part of the array contains the numbers 1 up to n over 2, that has a quadratic number of inversions, all of which are split. So what we're attempting to do here is count up a quadratic number of things using only linear time. Can it really be done? Yes, it can, as we'll see in the next video.